All right, good morning. Getting set up. All right, up front, if you're one of the 1 out of 5 students who did not submit homework 6, send me an email right away. Tell me what's going on. Because I don't know what's going on. But 20% of the assignments did not get submitted. So send me an email. Let me know what's up. I have office hours today at 2 if you're having problems with Git or problems with the assignment or something. Come by office hours. Let's screen share. Let's work it out. You gotta figure out how to make Git work and how to submit things through there and so on and so forth. All right. So any questions? I want to talk about ODP 452 and then play around more with GDB and then talk about strings. And then next week we're going to go back to some more advanced shell scripting. And if your assignment didn't get submitted, you've got a 0 on Canvas right now. So that's an easy way to tell. And if you don't have a grade entered, then I haven't graded it yet, but it got submitted. And I'm bummed I did not dress up for Halloween. I always dress up for Halloween at Clark. And this would have been awesome because it's a Friday. But I didn't get to it. Although we do have costumes. Alright, I got a screenshot. Cool. Alright, no questions? That could be how he always dresses for class, too. I don't know. It's all cool. All right. Well, let's talk about the ODP. Awesome. Yeah, that's good for coding too. In case, like bits fly off while you're editing them, it protects your eyes, which is important. I haven't looked at this code yet. This might be horrifying. I just wrote it a few days ago. All right, it's not too horrifying. So this was basically the code we went through yesterday, right? So this was mostly ODP 450. Started off by copying the input string to a holder, which I called old, and an output location, which I called J unimaginatively, and then looped through everything up through and including the null terminator, and copied from the old input string to the new and updated the output loc if either of the following was true. Either the old character was not an X, or we had already done our job of skipping one X. Right? So if done or that's not equal to X, then we went ahead and copied. And then just check to see if the character was an X, and if it was, set done to indicate that we had skipped it. So that's an example of stateful programming. All right. So we started messing around with GDB yesterday, and we did this in the guise of ODP 450. So I want to continue that. Add a few more variations on ODP 450. to work with. So we'll do more GDB. So I think we were up to clean3.c. Alright, so main3.c doesn't do anything productive. It wipes out our entire input string. So let's compile that with debugging. Let's say gdb main. Let's break at our clean function and say run. We'll put in an input of hello. And then we're going to use next or n to step through one at a time, one instruction at a time. So we copy new to old, we set our output location, we go through our loop, we check to see if old bracket I is equal to x. So old bracket I is x, and that's weird because my input string was hello. Alright, so I'm not sure what's going on. So let's just go ahead and say start, and that will start things from the beginning again, and it will ask, do you want to start from the beginning? Say yes, and I'm going to type in continue, and my input string HELLO. Okay, I'm back in clean. I'm going to copy from new to old. So let's print out new. New is hello. Let's print out old. Old is hello. Okay. We'll initialize outlook. And that's a 0. Everything looks solid there. We'll go ahead and step into our for loop, and we're about to say if old bracket I is equal to x. So let's print I. That's a 0. Let's print old bracket I. That's the letter H. Okay, that's not equal to x, so we should go into the body of our if statement. So I'll execute that if statement, and it looks like it went back to my for loop. Right, well I is 0, old is XLO. Right, so what's the problem here, right? So someone in chat found it. I'm doing a single equal sign here. Right. Now that's, a really hard typo to find late at night because, it looks like 2 equals, and when we read that and we're checking our logic, we're going to see that as, if old I is equal to x. We're not good at picking up those kinds of details. But running it through GDB, right, there's something funny going on right around here. And for some reason, right, this first character in my string got changed to an X. That will help nudge you towards, looking at this again and again and saying, oh my gosh, I can't believe I did that again. Alright. Alright, so let's look at clean 4. So clean 4, let's make that a double equal. Hello, hello. Hi, hi. And then hex, x, ox. Didn't quite work right. Alright, this is ODP 450. It's supposed to remove every occurrence of the letter X. Well, I tried hello and it worked, and I tried hi and it worked. And if I try hacks, it doesn't work. If I do HXA, it changes into HA with an A at the end. So this is almost working, but there's something weird going on. So let's debug it. And you get really good at this with if you're working on one particular set of code. You get really good at the routine of putting in the G switch, knowing what routine you want to break at, saying start, saying continue, going through like this, and getting to where you need to be. Alright, so our input string is HXA. We're about to copy that to old. We're about to set out location to 0. We're going into our for loop. Okay, let's check some things. Old is HXA with a null terminator. That's good. Output location is 0. That's good. I is inside our for loop. That's good. Okay, we're about to say if old I is equal to X. Let's look at old I. That's an H. It's not equal to X, so we should skip the body of this if statement, which was continue, and instead we copy the old character to the new. So let's do that copy. Let's print new. New still looks good. Let's increment output loc. Output loc looks good. So we're ready to write into character 1. Top of the for loop. Print the character I. It's a 2. Print old bracket I. That's the letter X. This should get skipped. There's our continue statement. And we go back to the top of the for loop. And the important thing here is our output location is still 1. Okay, this looks like it's working great. So one more iteration of the for loop. Let's take a look at I. I is equal to 2. Print old bracket I. That's the letter A. Good. Right? Old was HXA. We skipped the X. New, we wrote the H. We're about to overwrite that X with the letter A. Okay, so if old is equal to X, it's not, so we skip the continue. And here is new outlook equals old I. Okay, so it's going to copy the letter A into index 1 of new. Right? And there we go. We've got our H and we've got our A. We overwrote the X. Perfect. And then we increment outlook. And outlook's equal to 2. Alright, we're back at our for loop. We're done with our for loop. And we've exited. And now we should print out the value of buffer. Well, what is buffer? It's HAA followed by a null terminator. Well, guess what? That's exactly what new was inside our function. It was HHA followed by a new null terminator. But why is it HHA instead of HA? Because we wanted to remove the X. Our resulting string should just be 2 characters, H and A. So why does it have this extra character at the end? I know, it's Friday, and watching someone debug is not terribly engaging. Okay, it copies the next character of the string to the previous one to replace the X. Good. So the better question is why would that last A get cut off from my string? Nothing happened in my code to say, oh yeah, and don't use that last A as part of the string. We watched our code execute, and the only thing it did was copy an H to position 1, copy that A to position 2, and then return. It did exactly what we told it to do. It did not do anything more, but what we really wanted to do was end our string after that A. In other words, we wanted to null terminate it. And we didn't do that. Right? So there's really no such thing as a bug, right? Well, there are, but they're really rare. The machine will do exactly what you tell it to do, right? There's only sort of a misunderstanding or a miscommunication as to what you want it to do. All right, one more, clean 5. So let's make this less than or equal to make sure we pick up the null terminator. Right, so hello, that seems to work fine. Hexlo turns into hello, that seems to work fine. That seems to work fine. Never mind, clean 5 is fine. That was supposed to be the one with the missing equal sign. Let's look at clean 6. Alright, so we're doing less than or equal to. And yeah, just to chime in on the chat conversation, if I even look at my window the wrong way, it goes full screen. I think clicking anywhere, like in your window, makes it full screen. And I have a really hard time getting it out. There's a thing that says exit full screen, but you can't click on that. You have to click on the little symbol next to it. It's kind of challenging sometimes. Alright, so main, hello, and it turns it into an empty string. And if I put in X's, it turns it into an empty string. And if I start with an empty string, it turns it into something strange. And so this is clearly not working. So let's GDB it. So we'll say hello. Okay, we're inside our clean function, and there's what it does. Looks like it should work. Let's go ahead and single step through. So we're going to copy our new string to our old, set our output location, go through a for loop. We're going to check to see if the first character is an X, which it is not. It's the letter H. But then we go back up to the top of our for loop, and we check to see if the letter is an X, and we go back to the top of our for loop, and nothing is happening in our for loop. If it's an X, it should just continue out, but otherwise it should be copying our old string into our new string, bumping up the output location. That's not happening, even though I checked my old bracket I and it was the letter H, clearly not equal to X. But it's skipping my whole, all this code that I spent hours writing. None of it's getting executed. So what's going on here? Something's going on. So why is it not doing my copy in my assignment? Getting all kinds of ideas for exam questions. So finding the problem is a different matter, but the first point here is GDB is helping you isolate the bug, right? And we know that the reason our code isn't working is because we're not actually executing the body of our for loop, right? Even though our old character is not an X, it seems to be doing the continue. So this is a good one. I'm going to let you think about it another minute. Why are we skipping these statements? And it's not like the previous case where our string was changing because we had a single equal. Right? Our string is definitely not equal to an X, but it's skipping it for some reason. imaginary $1,000,000 bill. The continue is definitely not executing. If it actually executed that, we would see it when we stepped forward after this if. But that's a good thought. Ah, there you go. So there's no curly bracket after the for statement. And if you don't put a curly bracket after a for or an if, the body of that statement is a single statement. In this case, just this. So this is the only thing that's inside the for loop. And once I come out of the for loop, then I'm going to execute this instruction and this instruction and exit. Right? So that's a really horrifying bug to try to find. Right? But if you were to step through all the way, then you'd see these instructions executed afterwards. And then that can help point you there. So again, you know, a good debugger won't necessarily help you understand what the problem is, but it will certainly help you figure out where the problem is, at least for CSE224. 222, it's going to get more interesting because we're going to find bugs in our code that actually just kind of set up landmines. We'll sometimes do things in our code that are completely incorrect, but don't cause our program to fail at that point. But they set things up so that somewhere later we'll typically get a seg fault. And the reason for the seg fault will have nothing to do with the code around where the seg fault occurred. It will have something to do with something that happened in a different function, in a different file, in a different time. And that can be extra challenging to figure out, right? But we can still get there. All right, so that's some examples of using GDB to dig into code and single step it and try to find what's going on. There's limits to this. As I said yesterday, sometimes running something in GDB will cause it to miraculously work, and that's kind of a bummer. It's always nice to have a reproducible error. So if you know, once in a while you do something and your program breaks, right? Save what you've done, right? Go back and scroll through your history and make sure you can reproduce that bug, okay? And you know, I would say grab that code, paste it somewhere so that you have it, and then try to narrow it down to a simpler case that fails. And if you can get it down to, you know, run my program and put in like 3 lines of input and it blows up, now you got a good test case. You can put that input in a file, you can redirect from that to keep running that same test case, right? But you want to find something that exposes the bug. And then you can start going through GDB or putting in print statements or something and try to get that bug to come out. If compiling with GDB and running in GDB makes the bug vanish, then you got another problem. And you have to find some way to expose that bug inside GDB, or put in print statements or something that in a way that doesn't make the bug disappear. And that's just a reality of debugging and the real world. When I worked for Naval Research Lab, I was building a circuit board, and it was a wire wrap board, so like a breadboard, but that big, tons of wires in the back, right? and I was pretty sure it would work fine, but when I ran it, there was a problem with it. Well, it was in a rack of other boards, so you know you have all these boards sitting side by side, and you would take this board and slide it in, and it would meet with some connectors in the back, and there was a problem with it. So, you know, you get an oscilloscope and a multimeter, you can measure voltages at different pins and try to debug it, except that, you know, it's sitting in this rack with all these other boards near it, you can't reach it. So you get a board extender that basically slides in, and then you can attach your board outside of the others. Well, as soon as I put it on the board extender, the board worked perfectly. Right? Same problem. The extender was changing the timing just enough that a race condition I had went away, at least temporarily. So how did you debug that? Well, you got to find something else to do. So that can happen with GDB. But it will get there, it will get us most of the way there most of the time. Alright, so we'll come back to that from time to time and work more with it. Alright, questions on debugging GDB? So I did not give you an ODP today because you just finished homework 6 and you've had ODPs all week. And if you're in 215, I posted your programming assignment a few days ago. So there's a lot going on. So taking a break from ODPs today. We'll probably start back with some next week. And probably for more string processing. Let's see, I noticed you have a GDB video on your YouTube. Is that outdated because of updates, or could we reference it? No, that's a good video. The GDB that I talk about in class, and actually the GDB that I use, doesn't use anything novel or you know, particularly modern. And that old GDB video is perfectly valid. Everything in there still works, and that's pretty much, you know, for me, best practices for how to debug code. So yeah, definitely have a look at that if you like. And again, it's one of these things that you want to play with when it's not super critical, right? If it's the 11th hour, that's a hard time to start learning GDB. But you know, if you've got a week to get something done and you're running into some weird bug and you've got a little bit of time, it's a good excuse to start playing around with the debugger. And there's tons of references online that can help. There's, you know, pocket reference guides you can find and so on and so forth. And it's fun to mess with. Right, I mean, and you can do things like, you know, call functions inside here. Alright, debug.com, cool. I'll have to check that out. Someone says they spent a good few hours in there. You can do things like lay out ASM and switch to an assembly language mode, right? And now we're looking at the assembly language. This is x86 code because I'm on an x86, corresponding to, you know, our program that we've been debugging. And you know, I can say step a single instruction, and all right. So yeah, these are the low-level instructions that kick in when you run your program, right? This is what your code got first compiled into and then assembled into. These are offsets from the beginning, which is main. You can see that, you know, some of your instructions like push take a single byte because the next instruction was main plus 1. Some of them, like this move instruction, take a whole lot of bytes because this is at main plus 8 and the next instruction is at main plus 17. So this was a 9-byte instruction, right? So x86 processor is a complex instruction set machine, different length instructions. PIC processor is a RISC machine. All of your instructions, with a few exceptions, are the same length, 2 bytes, 16 bits. So call Q is a call instruction, but it's probably called quad word. And I don't know if that's referring to the argument or the address. But usually Q is for a quad, B is for a byte, and so on. This is a decent way to learn or brush up on assembly language, right? And you can print your registers. So there's the program counter. There's the EDI register. We can print it in hex. Right? I don't know what EDI is, but we're about to use it in a move instruction, right, down here at main plus 53. LEA is a load effective address, so that takes the address of something and loads it in. That's kind of like an ampersand, right? And if you really want to go deeper with some of this stuff, right, write yourself a really simple program in C that does, 2 or 3 things. Forget about function calls, because function calls are complex, and run it in the debugger doing layout ASM and see what it looks like. The other thing you can do is, GCC -C-S and put in the name of a C program, and that will get you a .s file, so clean.s, and that's the assembly language version of your code. And this is a little higher level than what you see in GDB, because GDB is running off the executable. But you can see your file name here, you can see labels, and so on and so forth. And that can be interesting. There's a call to string length. GCC-uppercase-S is the way you get to the preserve the assembly language. Because what does GCC do? It basically converts your C program into assembly language and then assembles that, right? But it gets rid of the temporary file. I think it just does it in memory, actually. And so the -S says, keep the temporary file around. And then if you want, you can assemble as clean.s. And that'll assemble it into an a.out. Which I don't think will run. Yeah, that's a little weird. Right, but clean.c doesn't have a main program, so. All kinds of things you can play around with this. Before Google, before a lot of technical books were published on this stuff, this was the way that you learned how computers work, right? And it's still a viable option. If all you have is your laptop and the manual pages, in a Linux system, you can explore all of this stuff. And I think it's a lot more fun than just, listening to lectures on YouTube or reading page after page after page of something. Get in there and get your hands dirty and pull this stuff apart and put it back together, What happens if you change one of these offsets or change one of these instructions, Can you modify what the program does by tweaking the assembly language? Or can you do it in the debugger? And, I can look at the program counter, that's clean plus 19. I can examine what's stored in memory at the beginning of my clean function, and, it's a bunch of hex. Well, those are the ones and zeros that make up my machine code. Starting right here, that's the binary machine code. So if you did 270, right, you take your assembly language instructions, you look up in that table 20-1, you translate each of those instructions into ones and zeros. This is what you get for an x86. And if you do an examine/I, that'll also show you the assembly language. So that's my clean function. And this gets you into the question of how do you pass things to a function, right? When I call a function and I give an argument to it, how does that information get passed on to the function that I'm calling? When I return from a function, how does my return value come back to my main program, right? All of that is exposed in here. So operating system course, system programming course, digital forensics course, any of these things, you'll start digging into this more and more. And one of the tools that you use most often for doing this is GDB, right? So you'll encounter this stuff again and again. All right, we got 10 minutes left, so let's switch gears and go back to talking about Unix a bit. So one thing to realize in Unix is pretty much everything is a file. So we know that we have files that we create with VI or with GCC or something, and there's files like that, but everything on the system is a file. Your directories are also files, right? So if I do an ls-l, any of these things that starts with D in the beginning, that's a file, right? And I can VI Titanic. Well, VI knows that this is a file, a directory, so VI will actually interpret the contents of that file and show me what's in the directory. But if I do something like xxd, which just gives me a raw hex dump, oh, it won't do it. Oh, well, that's a bummer. Well, if you open up the file and use reads, you can see the binary stuff that's in there, okay? But it's just another file. If you go into the /dev directory, there's all these things in here. These are all files. But they're mostly files that are actually related to devices. So CD-ROM is, if there was a optical drive on this machine, that would be right here under SR0. And it's just a file. You can open it up with fopen. You can write to it with fprintf. You can read from it with fgets. You can fclose it. You can open it with lower level functions like open, read, write, close. But it works just like any other file, except that when you read and write and open and close this particular file, you're interacting with a piece of physical hardware. This is my standard in. So when you do an fgets and you read from standard in, what is standard in pointing to? Standard in is what we call a link. We're going to talk about links separately. It's a link to this file, /proc/self/fd/0. So if I go under /proc/self, there's a whole bunch of files in here, right? Some of them are just plain files. Some of them are what we call links. Some are directories. But this is all stuff about my current process, right? What's my current directory? Well, my current directory is this. What are we using to execute things? We're using bash. If I go into FD and I look at my file descriptors, I have 4 file descriptors. 0 is standard in, 1 is standard out, 2 is standard error. But standard in is actually something called /dev/pts/0. It's another device. Ultimately, when you try to do anything on a computer that gets outside of the box, when you try to do input or output or talk to the network or read a mouse or something like that, something needs to make that connection between your code, which is saying fgets, and perhaps a keyboard that somebody is typing into. Well, those are mostly done through things in this /dev directory. And PTS, that's a pseudo terminal. And PTS/0 is the pseudo terminal associated with my keyboard, right? And if I redirect my input, I'll see something new in this FD directory, which will tell me where my output should be going instead of PTS/0. So all the essence of your process, your interactive shell, is set up in this directory under /proc, including your memory. And there's this file under /devs called mem. I haven't monkeyed with this in ages, but at least at one time this actually was the memory of the machine. And you could go in there and you could open it up and you could pull information out of there and you'd be reading main memory. And it would transcend process boundaries and permission boundaries and all that kind of stuff. Now this is set to be inaccessible to the world. But if you're a root user, you can read it and you can write it. If I write something into there, the machine will probably crash. At the very least, my process will crash. So everything is a file. And that's convenient because it means your mechanisms for interacting with hardware are the same mechanisms for interacting with plain old disk files. Open, read, write, close, seek, flush, etc. You don't need separate functions to push something out to a network connection or to send something to a printer, right? All of those things are managed through the same functions. It also means that your protection system comes down to, can you protect access to files? So somebody needs to be able to write to the hard drive, but we don't want a typical user to be able to do that directly because you could read other people's files, you could corrupt the system, and so on and so forth. So, so hard drive access is controlled by simply setting the permission bits on the hard drive device. So everything in Unix is a file. It's a subtle point. It's also an obvious point, but it's important to keep in mind. And all of our files are located under this top level directory, which is called the root directory, unrelated to root permission per se. But this is the root of the file system. And it really only has a few things in here. And of those few things, only some of those are directories. There's a few links. All right. So under /boot, you find the files that are used when you try to start up the machine. /bin is most of our executable programs. Dev are the hardware devices, etc. is largely maintenance-related files that are used by the system, and so on. Home is where all of our home directories are stored. Subdirectories of home. Lib and lib64 are where things like the runtime libraries live. So when you compile a program that calls printf, where does the code for printf come from? It comes from a library. Media and mount are where typically external devices show up, like when you plug a USB into a laptop running Linux, you'll get a new file under /media or /mount. And so on and so forth. Temp is a temporary space. User is a space with more executable programs and manual pages and include files and all kinds of things like that. SBIN is usually programs that are used by the supervisor, by a root user. And then these things are related to booting up. All right. Symbolic links. We'll talk about these more on Monday. But when you do an ls-l and you see an L in this first column, this is what's called a link. And it means that if I try to access this file, in fact, I'm accessing this file. It's basically a file pointer in some sense. And it lets us change what the nature of this file is by just changing what it points to. And this happens a lot with versions of code. For example, right now, this refers to version 4.4.0-103. If that changes at some point, it should be 4.4.0-107, right? Anything that's looking for that file still just looks for init.rd.image. But we can change, that to point to a new version, and anything that worked before will still work. So yeah, you can make a Dropbox folder on your Linux system, set up a link for it. A lot of things are really links. If you look at VI, it's just user bin VI. But if you actually look at what that is, that's a link. And it goes to /etc/alternative/VI. And if you look at that, that's another link. And it goes to user bin vim basic. And that's, I think, the actual VI program that's being executed. But if I wanted that to be vim.tiny, I could simply change this link, and suddenly everybody who says VI would be running vim.tiny. So a lot of this stuff is links, right? There are real files, like this is a real file, but yeah, a lot of the stuff is just links. And especially commands, like GCC, that's a link to GCC-5. If there's a new version of the C compiler, GCC-6, I could change this link, and you would still say GCC, but you'd be running a different version. All right, so we'll call it good here. Have a good weekend. We will dig into deeper bash scripting next week. Look at more constructs, we'll look at associative arrays, and then we'll start digging into things like awk and sed and some of these other powerhouse tools. All right, have a good one. See you then. Thanks.